Good day, I'm Norman Wildberger. We're on our way to examining and ultimately deflating the modern theory of sets. Before I do that, I would like to give you an alternative point of view towards set theory, and in fact more generally to other kinds of data structures in mathematics. That's what we're going to start doing today. So I want to set up a much more careful, much more precise, much more concrete approach to how we organize things in mathematics. Okay, so set theory is an attempt to organize mathematical objects. At least that's certainly one of its aims. And this is parallel to attempts to organize physical or real-life objects, to classify things, to put things into containers in such a way that the structure is more accessible. So there are also obvious connections to computer science. All right, so I remind you that the standard approach is that, well, the fundamental kind of object is that of a set. And here's the standard way of thinking and writing down a set. It's an object that you get by taking these curly brackets, sometimes called braces, and then you put a few elements in and you separate them by commas. And we agree that this notation means that this set is unordered. That is, if we rearrange the order of these elements, the set has not changed. And we also agree that we're going to not allow repetitions, so that each one of these elements can only appear once in the set. All right, in this video we're going to look at sets, but in the context of a wider view of data structures more generally. We're going to see that sets are just one of 4 different types of important types of data structures. And we're also going to introduce some novelty into the laying out of this theory. And in particular, we're going to have to say goodbye to this notation. We're going to let go of this notation for a set. Now, those of you who've been watching my channel for a while know that I'm not afraid of going off in different directions and introducing new notation and ideas if they're necessary. And this is a situation where it is, I think, necessary to have another look at exactly how we write things down. Notation is very important in aligning with our understanding and allowing us to move forward smoothly. So here's a chart that lays out the 4 different possible kinds of data structures that we're going to be emphasizing today. Okay, so there are actually 4 kinds of objects called sets, ordered sets, multi-sets, and lists. And they're characterized by these 2 different properties. The property of either being unordered or ordered, and the other property of being either without repetition or with repetition. So let's have a look at these 4 possibilities. The one that we're mostly familiar with is that of a set, which, as we've said, is an unordered object. It doesn't matter if we permute the elements. And it's also without repetition. We do not allow things to be repeated. Now have a look at this new notation for a set. Okay, still has the curly brackets or braces, but now there are no longer commas separating the elements. There are just spaces. This suggests that the elements are in fact not in a particular order. They're kind of freely floating inside this box. So the absence of commas makes it easier for us to appreciate that we can rearrange the order of these things, and the set is not changing. Set in quotation marks, so we haven't actually defined these things here. I'm just introducing the general framework and the notation that we are going to be using for these 4 kinds of things once we get around to defining what they are precisely, which I will do later on. Okay, a variant of that is this thing here, which is an ordered set. Okay, so this is same kind of notation that we're actually familiar with, but we're going to agree that this means something which has no repetitions, but which is ordered. The presence of the commas means that we're seeing a first element, a second element, and a third element. So it's like a set which has been ordered and the order is fixed. Over here is something which we call a multiset, which is like a set in that it's unordered, but it's different from a set in that repetitions are allowed. So here we see a 1, a 4, and a 2. There's no commas. These things are freely floating around here. We can rearrange the order, but we are allowing 2 1s. And the brackets now that we have are different from the ones that we had there. We have actual brackets instead of braces, and it's this bracket notation or convention that's going to signify for us that we are allowing repetitions. And the fourth possibility is when we consider data structure where repetitions are allowed and which is also ordered, and that's a list. So a list like 1, 1, 4, 2 is given in the square brackets, the same as a multiset, but now the commas here are alerting us to the fact that this thing is ordered. There's a first one, there's a second one, there's a third one, and there's a fourth one. So I'm proposing that we adopt this notation to, generally speaking, deal with these 4 different types of data structures. Yes, it's unconventional. Yes, it also makes a lot of sense. So when it's a matter of convention versus making sense, which direction are we going to go in at this channel? You all know. Common sense trumps convention. So this is the way we're going to think about sets, ordered sets, multisets, and lists once we define what they actually are. Okay, so to reinforce what I've just said, we've introduced these 4 notational devices. Braces to represent a data structure where repetitions are not allowed, and square brackets to represent a data structure where repetitions are allowed. So curly brackets, no repetitions. Square brackets, repetitions okay. And we're also introducing the idea that a space between elements represents the fact that those elements are unordered. We can permute them around. They're freely floating inside the box. There's no structure or sort of container aspects inside the box, compartments. There aren't any compartments. These things are just there, separated by space, allowing them to move around. That's unordered. And if we want something that's ordered, a first, a second, a third, we're going to separate those elements by commas, and we're going to put them in the right order with commas separating them. Okay, so let's just solidify our understanding of these things and have a look at some examples. So do we have sets, ordered sets, multi-sets, or lists here? Okay, what about A? Well, the curly brackets means that repetitions are not allowed. And there's spaces here, so it's unordered. So it's unordered, repetitions are not allowed. This is a set. How about this thing here? Well, the square brackets means that repetitions are allowed, and the commas means that things are ordered. So this is a list. How about this thing? It's got some curly brackets, so it's without repetitions. And does it have spaces or commas? Well, we can't really say because there's only one element, the element 27. So this could be a set, or it could also be an ordered set. Maybe I'll write O set for ordered set. The form of it is not completely defining what kind of object it is. How about this thing here? B equals square bracket 7. So square brackets means repetitions are allowed. So this could be a multiset, or it could be the beginnings of a list. But we don't know whether there's spaces or commas. It's not really relevant because, again, there's only one element. How about this thing here? C equals 5, 4, 3, spaced with commas. Now this is the traditional notation for a set. But in our notation, the curly brackets means that it's without repetitions, and the commas means that it's actually ordered. So this is actually an ordered set. All right, O set. It's not a set, it's an ordered set. How about this thing here? The square brackets means that repetitions are allowed, but there are no commas, there are spaces. So we can move things around. This is a multi-set. How about this thing here? Just square brackets with nothing inside it. Well, that's probably going to be a little bit ambiguous because it's square brackets, meaning that repetitions are in principle allowed, but there's no elements that are being repeated. But nevertheless, this could be either a multi-set or a list. So the empty multi-set or the empty list, if we're eventually going to define those things. How about this thing here? It is a bit more complicated. It's got square brackets and commas. That means it's a list. Okay, the square brackets means that repetitions are allowed. In this case, there aren't any repetitions, but nevertheless, repetitions would be allowed. And the comma means that it's ordered. So this is a list. In fact, it's a list containing two elements. The first element is a set or an ordered set. And the second element is a list also. And finally down here, J, we have square brackets, so that's with repetition, so it's either a multi-set or a list. We look, are there spaces or commas? There are spaces, that means it's a multi-set. We can move things around. So it's a multi-set or M set. In fact, it does have some repetition. You see that one of its elements is the multi-set 2, 3, and that element is the same as this one here. This one looks different, but this as is a multi-set because it's separated with a space, those 2 and 3s. So this multi-set and this multi-set, they're actually the same. So J itself is a multi-set with 3 elements, but these two happen to be the same. Okay, we have not yet defined exactly what we mean by sets, ordered sets, lists, or multi-sets. Okay, we are just establishing at this point notation for those things that we're about to introduce. I want to emphasize the notation first to get you used to the idea that we can structure data with curly brackets or square brackets and with spaces or commas, and that each one of those things can mean something separate, so that we're covering all 4 possibilities, ordered or unordered, with repetitions or without repetitions. Okay, it's nice if mathematics reflects the real world, and these 4 kinds of data structures are very much reflecting what actually happens in the real world, and they're very useful for us to apply to various situations to organize things. Okay, so let's have a look at some examples of data structures in real life and sort of correlate them with one of these 4 types of mathematical data structures that I've outlined, just to give us a preliminary sense of how these things could be used. Okay, there's a little bit of ambiguity here because we're talking about the real world. Possibly one could reinterpret the questions and so on. Okay, suppose you have people in a company. You have some big company, and we're interested in the collection of all people. Now, what kind of a collection is that? Well, first of all, is it ordered? Is there naturally a first person, a second person, a third person, up to a 3,000th person? No, it's probably not. There might be a CEO and so on, but it's not true that we can give a linear ordering to all the people, so it's essentially an unordered structure. And what about repetitions? Are we allowed to have 2 different people which are actually the same? No, all the people in the company are distinct. So this is an example of a set. How about the names of people in a company? So we take that same company and we just write down all the names of all the people. Again, this is unordered. But now there's definitely the possibility, especially if it's a big company, that a couple of different people are going to have the same name. So there's going to be repetitions in the names of the people. That makes it a multi-set, or M-set for short. How about words in a dictionary? So just the list of words, the A words, the B words, the C words, and so on. Well, those words are all distinct, and they're definitely ordered, because that's the whole point of a dictionary. So we have distinct words which are ordered. That's an ordered set, which for short we might say is an O set. How about letters in a word? Okay, so we look at a word, and we look at the letters in that word. Well, that is definitely ordered. Right? For example, if the word happens to be letters, then there's naturally a first letter and a second letter and so on, so it's naturally ordered. And repetitions are in principle allowed because a letter can appear more than once in a word. So this is naturally a list. How about web pages? Look at all the web pages that are around. Well, they're all distinct. They have different URLs. And are they ordered? No, they're not ordered. So this is a situation where we have distinct things which are unordered. This is a set. How about images found on the internet? Just look at all the images that are found on the internet. Again, unordered, but it's very possible to find the same image in different places. So we have repetitions. Unordered, but with repetitions, that's a multi-set, or M-set. Okay, what about primes from 2 to 19? Okay, one can think about this different ways, but probably the most natural is to think of it as something that's ordered, because it is sort of reasonably naturally ordered in terms of increasing size. And they're all distinct as well. So this is really an ordered set, primarily, I suppose, or O set for short. And finally, the bus numbers that arrive at a stop. So you are at a stop and buses are coming, and you're just recording the numbers of the buses that come. Well, obviously there's an order to it, and repetitions can occur because the same bus number can come consecutively sometimes. So repetitions are allowed, but it's ordered, so this is a list. Well, it's fun to look around at different examples in real life. You might like to do this yourself. Have a look at various things that come around and say, well, is this particular thing a set, an ordered set, a multi-set, or a list? Just to get used to thinking in terms of these 4 different categories, ordered or unordered, with repetitions or without repetitions. All right, so while there are a wide variety of different kinds of elements that occur in real-life data structures, for us, we want to constrain ourselves to a much more precise and sort of concrete framework. So we're going to work, at least initially, with natural numbers. And natural numbers augmented slightly to include 0. When we do that, we'll put a little plus sign over the type to specify that we're including 0. And we're going to agree that since we want to be able to communicate completely precisely with each other, that we're going to restrict ourselves to the Hindu-Arabic form of a natural number. So if n is in natural numbers, or k is in natural numbers augmented with 0, there's only one way of writing such a number down. So let me illustrate that with an example. So n equals 13. Okay, this is the Hindu-Arabic form for the number 13. 3 ones, 1 10. Okay, so we're going to like this way of representing things. We're going to agree that as far as set theory and building up set theory is concerned, these other ways of representing 13 are not going to be allowed. So we are not going to allow that this 13 is represented in a data structure by the expression 12 plus 1, or by the expression 1 plus 1 plus 1 plus 1, etc. plus 4, or by some statement like n is the smallest prime greater than 12, or by some even more ambiguous statement like n is Mary's lucky number. Because if we allow that kind of thing, then we would have to have a secondary whole discussion about what kinds of expressions are allowed and how to tell whether your expression is the same as Jerry's expression is the same as my expression. Okay. We don't want to do that, so we want to agree that there's exactly one way of specifying a natural number. And in the same spirit, if k is 57,109, we're going to agree here in this discussion that we're going to represent that this way, in particular without commas. Okay, so we're going to go for that expression. We are not going to allow an expression where there's commas, because we're going to use commas to separate elements in things like lists or ordered sets. And if we have commas in the numbers, there's at least possibility of confusion as to which meaning the comma is being used for. So let's just agree that when we represent a number in Hindu-Arabic form, we just write it in the usual form without any commas anywhere. And also, we're not going to allow decimals. So although in ordinary life this is the same as this, to all intents and purposes, but for us, when we're actually representing numbers in our data structures, we're not going to use this form to represent that natural number. Okay, so we're just going to make this agreement. So that means that there's only one way of writing down a natural number. We can all agree on that. So let's start. Our first data structure, perhaps surprisingly, is not going to be a set. We're going to start with the idea of a list. In particular, we're going to start with something that we call a k-list. Okay, so the setup is that for n and k natural numbers, okay, so we choose an n and we choose a k. We're going to define a k-list from n. Right, so this is the object that we are about to define, what it means to have a k-list from n, like a 3 list from 5 or a 17 list from 3,000. Okay. That's going to be defined to be an expression of the form L equals square brackets inside M1, comma M2, comma M3, comma and so on, comma all the way up to Mk, where each of these mi's is a natural number and furthermore is somewhere between 1 and n. So the range of possible values for these elements is 1 to n, restricting ourselves to only natural numbers. And there are altogether k of them. So we've chosen n and k to begin with. The n tells us the range of values that the elements can take on, and k tells us how many there are going to be. So this is a new type of mathematical object, which we are going to call list. And list nk, because it depends on n and on k. So for example, here is such a k-list. This is actually a 3 list because it has 3 elements. It's an element of list 4, 3. So the actual elements are in the range 1, 2, 3, and 4. And they're ordered because there are commas. It's a list because there are commas and square brackets. It's an element of list 4, 3. So this is a 3 list. A 3 list from 4. Here is a 1 list from, say, 15. It's also a 1 list from 14 and also a 1 list from 13. It has 1 element, it's got square brackets, so that's a bona fide 1 list from 15. Here's a 4 list from 5. There are 4 elements, but there's some repetition, but they're ordered. ordered with repetition allowed. We're talking about a list. So this is an example of a for list from 5. And here's an example of a for list from 2. Okay, so the conventions are very important. We're talking about square brackets. We're talking about having the elements separated by commas. That's our convention for a list. And now we're being more precise. We're saying that we're not going to talk about a general list. We're going to only talk about a k-list from n. That's what we know we have so far. We do not have the general notion of what a list is. We only have the notion of what a k-list from n is for a particular k and n, which are natural numbers. Okay, here we come to a little bit of a subtle point. So we're going to define what we mean by elements of a list. So the objects, which are natural numbers, m1 up to mk, which appear in the k-list L equals m1, m2 up to mk, are called the elements of L. So m1 is an element of L, m2 is an element of L, all the way up to mk is an element of L. Each one of those is an element of L. They are considered as distinct elements, even if as numbers they are the same or equal. So this is a bit of a subtle point, so let's look at an example. So here's a for list L. It's 3, 1, 3, 2. It's a list. There's some repetition. There's 2 3s there. Okay. So this thing has 4 elements. That's an element, that's an element, that's an element, and that's an element. When we write them out as elements, you can say, well, these 2 are the same. Really, there should only be perhaps 3 elements. But no, we're not going to say there are 3 elements. We're going to say that there are 4 elements because we're going to regard this 3 and this 3 as being distinct, even if they are the same as numbers. And then we're going to define the size of the k-list L to be the number of elements, namely k. So if we have a k-list, then the size of that k-list is necessarily k, independent of what the elements are. So I think I could provide a lot of evidence for the claim that the list is actually the most fundamental data structure. The list is actually more fundamental than that of a set or the other ones. So then we move to another one, which is the ordered set. So this is a variant of a list where all the elements now are required to be distinct. So an ordered set is a list, all whose elements have to be distinct. So here's the official definition, and it follows the same kind of agenda as for lists. So for n and k natural numbers, a k-ordered set from n is an expression of this form. O equals, okay, now there's our brace brackets, curly brackets, with an m1, comma, m2, comma, m3, comma, all the way up to comma, mk. So it's just like a list except that it has curly brackets instead of square brackets. And the curly brackets are telling us that repetition is not allowed. So each of the mi has to be a natural number, still has to be within the range 1 to n, because this is a k-ordered set from n. But now there's an additional requirement that the mi are all distinct. And we can say that mi is not equal to mj if I is not equal to j. Here's an example O equals the ordered set 1, 3, 5. This is an ordered set 5, 3. So it's actually a 3O set from 5. And it has 3 elements, which is the k. So we also use the same convention for size as we do for lists. All right, so from now on, a thing like this is actually an ordered set. The commas here representing the fact that we have decided to order the elements. That's in fact what the commas sort of do for us, don't they? The commas are ordering the sets, so it's no longer the case that here we're going to be allowed to interchange these things and say, it's the same thing. No, the commas mean that the order matters. So another variant of a list, in a sort of different direction, is that of a multiset, where the order is no longer important, but repetitions are still allowed. So here's our definition. We're going to talk about k multisets. And again, starting with n and k natural numbers, a k multiset from n is an expression of the form M equals square brackets M1, M2, all the way up to Mk, where now there are only spaces between the elements M1, M2, and so on. There are no longer commas. So this kind of expression is defining a new kind of object, which we'll call an M set Nk. And the m's have to satisfy the following things. They have to be natural numbers, and as before, they have to be within the range 1 to n. And now in addition, the order of the elements mi is unimportant. If we interchange the position of m2 and m1, then we agree that the multiset has not changed. So we interchange any two elements, we can rearrange those k elements however we like, and we agree that we have the same multiset. So for example, here is a multiset 1, 3, 3, 1, 15. It's the same as the multiset 15, 1, 3, 1, 3. Same elements, different order. So we say that this is a multiset, or a 5 multiset from 15. And this is the type that we'll use, M set 15, 5. And the size of M is, as before, the number of elements in here, which is 5. Even though this 3 appears twice, these are both counted separately when we're talking about the number of elements. Okay, and finally, what is a set? Well, in this context, we're going to talk about k-sets. Again, the starting point, n and k natural numbers. So we're going to define a k-set from n to be an expression of the form S equals, curly brackets, M1, M2, all the way up to Mk, with only spaces between the elements Mi. It's going to define a new kind of type called set Nk. And the condition on the mi's, well, as before, each of the mi's are natural numbers. They're all in the range 1 to n, and they're all supposed to be distinct, just as they were for an ordered set. But now, in addition, their order is unimportant. There are no longer commas between them as we have for an ordered set. So now that means you can rearrange them without changing the nature of the object. So for example, S equals 13, 7, 2, which is the same as 2, 7, 13. This is a 3 set from 13. So we can write it belongs to set 13, 3. And the size of the set is the k value, which is 3 in this case. So notice that the order of the 4 types that we introduced started with list, then ordered set, then multi-set, then set. The set was in fact the last one, and it's really the most complicated one. It's the most complicated because the conditions on the mi's, there's 2 conditions. We want them to be all distinct. In practice, that requires a lot of checking. And we want their order to be unimportant. That means you have to have some way of being able to tell whether somebody has come along and permuted your trillion elements in your data set, and and whether it's still the same or not. So from a computer science point of view, a list is much simpler than a set. So we're kind of going in order of maybe complexity from a computer science point of view. Okay, so there's a lot more to be done now. So we've at least had an initial orientation framework for dealing with data structures of an admittedly very specific and focused kind. But it will turn out that each one of these 4 types of data structures supports a very rich theory, very rich combinatorial theory, and we're going to talk about that. So we'll have plenty of evidence to show you that this is a very rich topic here, and we don't need any kind of fanciful axioms. Okay, there's no axioms in sight. We're just defining things. Everybody can agree, everybody knows exactly, once you've adopted the conventions, that this is a set but not a multi-set. There's the possibility of really having a broad agreement right across the board here. That's what we want in pure mathematics. It doesn't have to depend on philosophical positions or axiomatic systems or other belief systems. I want to get rid of all that. Okay, so next time we're going to start building up some of the additional theories that each one of these data structures supports. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.